Welcome. In this video, we will take a look at the idea of sector area. So let's take a look at developing its definition first. We'll take a look at the area of a circle, which is formed by the area equals pi r squared. So we can highlight this. Pi r squared is just the area of a full circle. And really what we're after here with the sector area is a portion of that area of a full circle. So just a portion of that. So when we consider a portion or just a sector of a circle, we have that image on the right side here. This is really just some fraction of the circle, and we want to find its area. And so when I consider the kind of the fraction of this circle, remember that our full circle has 2 pi radians. And so when I consider what fraction of a circle this sector is representing, this is really what we would call theta, whatever that angle is, divided by 2 pi of that circle. Right? So a full circle would be 2 pi radians, and we're just going to be choosing theta radians, whatever that theta angle is going to be. So that's the fraction of a circle that we want to find area of. And so when we define this, so the sector area of a circle, again, is just going to be a portion of that full area of the circle. And so when we define this, the area of the sector is found by that portion, that's theta divided by 2 pi, that's the portion of the angle, times the full area of our circle, that would be pi r squared. And so when we multiply those through, we get a final equation for the sector area of a circle, which ends up being 1/2 times the theta value, that's the central angle, times r squared. Let me highlight that actually. Where theta, again, is measured in radians. We want to always measure our theta angle here in radians, just like we use radians for our arc length. So let's just do one kind of check here for this equation. What if we did consider a full circle? Full circle. Sitting right here, we have a central angle of 2 pi and a radius of r. If our central angle here is 2 pi, we could say that the area is going to be 1/2 times the theta is just 2 pi, that's our central angle for a full circle, times r squared. Notice that those 2's will cancel, and we're left with the area of pi r squared, which is, again, the area of a full circle. So this actually matches up perfectly with what we would think a full circle should have as its area. So we can trust this formula and the logic that's behind this one for the sector area. So let's now use this formula and work with it carefully. Again, we want to make sure that all of our angles that we use are going to be in radians. So this first example, we want to find the area of the sector formed by a central angle of 210 degrees in a circle of radius 3.5 meters. Okay, so the number one thing that we need to do here is consider converting this angle, 210 degrees, to radians. So let's consider doing that first. We know that 210 degrees can be converted to pi radians over 180 degrees. We'll notice that each of these values, 210 and 180, have a common divisor of 30. So that would be common divisor of 30 would give us 7 and 6. So this is really 7 pi over 6 radians. And again, we know that the radius is already 3.5. We don't have to change that for meters. So let's look at the sector area. Sector area is going to be, we'll just call it SA, sector area. Not to be confused with surface area, but just talking about sector area, we have 1/2 times the theta, which is 7 pi over 6 radians. And then our radius squared would be 3.5 meters squared. All right, so this will give us two things. We're going to need to square the 33.5 and also square that unit. So our sector area here does have squared units at the end. And for this one, we'll just round to the nearest decimal. If you were able to put this into your calculator, again, we're going to be squaring 3.5, multiplying through by 1/2, and then 7 pi over 6. If we put this in our calculator, you'll find this is going to be approximately 22.45 meters squared. So that would be our approximate solution. We could put approximation there. Let's take a look at one more area of the sector example. We want to find the sector formed by a central angle of 15 degrees has an area of pi over 3 centimeters squared. We want to find the radius of the circle. Okay, so let's consider the little picture here. We're going to have a very small central angle. I'll blow this up a little bit so we can kind of visualize what we have. So the central angle is just 15 degrees. And we know the area is that 3 pi over 3 centimeters squared. And we'd like to find the radius r here. Okay, again, we have angles and radians kind of mixed, so we'd like to convert this 15 degrees to radians. So 15 degrees to radians, pi over 180. 15 is a divisor of 180, and if you divide that in evenly here, you'll find that that divides into 12 times. So we have really 1 over 12. So we have pi over 12 radians here. So let's set up our equation here to solve for our radius. We know that the area of our sector is equal to 1/2 times theta times our radius squared. So we'd like to go out and find that radius, so we have the angle and the area. So this would be pi over 3 centimeters squared equals my theta times 1/2. And then we have r squared. So let's continue to work with this. We have pi over 3 centimeters squared. We'll have pi over 24 times the radius squared. If I multiply both sides here by 24 over pi, with that reciprocal, we can get r squared by itself here. That would be 24 and 3 give us 8 as a divisor, or the quotient. This will be equal to just r squared on the right, and let's just keep that units in there just to remind ourselves as we go. So if we have 8 equals r squared, we know we can take a square root here. of both sides. And since we are working with a circle, we know we're going to be taking the positive root from this. So if we take a look at the square root of 8, we'll just take the positive root from this. And you'll find that this is just going to be 2 roots of 2. You can write it like that, or the square root of 8. Centimeters is going to be our radius. So we have 2 roots of 2 for that radius value. And that's just going to be in centimeters, unit length. All right, and that would be the conclusion for this problem. 2 roots of 2 centimeters would be the exact solution for that radius. So, thanks for watching. In the next video, we will talk about the linear and the angular velocity. Thanks for watching.